All right, we're going to move on from what we were doing yesterday, which was on phases, and go into phase changes. So tomorrow in class, your focus is going to be on being able to differentiate between these exothermic and endothermic phase changes, and relating how particle distance, attractive forces, and energy are all involved with these phase changes. So one thing I want to point out that you're going to hear me keep referring to is how IMFs are related to these phase changes. Whenever you have a phase change that involves particles moving farther apart, they have to actually absorb energy to overcome those attractive forces that are trying to keep them together. So you're going to see whenever we move from a solid to a liquid, or a liquid to a gas, or even from a solid to a gas, they need extra energy to move farther apart from each other. And then the opposite is true when we have phase changes that involve particles moving closer together. They have to get rid of that extra energy in order to slow down and be able to exist next to one another. So this allows the attractive forces, when we lose that energy, to be pulling the particles closer together. Alright, so we're aware of our phases, solid, liquid, and gases, and you should be familiar with these terms that I have up on the screen in terms of their phase changes. Melting and freezing are phase changes that exist between solids and liquids. Vaporizing and condensing are phase changes that allow us to move between liquids and gases. Now, as we go from a solid to a liquid to a gas and we move the particles farther apart, as I said in the 2 slides ago, this is an endothermic change. They have to absorb energy and either to melt or vaporize. As the particles need to move closer together, such as when they condense or freeze, they need to get rid of extra energy in order to slow down and move closer together. And that's an exothermic phase change. So phase changes are always going to be classified as either endothermic or exothermic. So you have this chart in your note packet. We're going to work on the left side first. So phases involve solids and liquids. Well, when it's an endothermic change, the particles are going to move farther apart, so this is when a solid goes to a liquid. You should already be aware of melting. However, we can also call this endothermic change fusion. When we go from a liquid to a gas, this can be classified under vaporization, boiling, evaporation. So again, liquid to a gas, it's going to have to absorb energy. And finally, we can actually have particles that go from a solid directly to a gas, and we refer to this as sublimation. We'll go over some great examples in class tomorrow. All 3 of these endothermic changes have to absorb energy in order to overcome the IMFs that are trying to hold those particles and keep them together. On the right-hand side, we're going to focus on exothermic changes. So here we have from a liquid to a solid, the particles have to slow down, move closer together, and we refer to this phase change as either freezing. You can also see it as solidification. When we go from a gas to a liquid, again, particles which are really far apart from each other have to come together and exist very close together. This is called condensation. Again, those particles are going to have to remove and get rid of energy. And finally, we can have particles go from a gas directly to a solid. This is called deposition. And again, we'll go over some great examples of this that you've seen before in your everyday lives tomorrow. All 3 of these exothermic changes have to release energy, which then allows the IMFs to pull those particles closer together. So keep that in mind about how IMFs apply to each of these endo and exothermic changes. Now, one thing I'd like to point out at this point when we're talking about all these different phase changes is the temperature at which they occur. Boiling and condensing both occur at the boiling point of water. So water can both boil at 100 degrees Celsius or condense at 100 degrees Celsius. Now, which phase change occurs depends on whether energy is being added or taken away. This is also true about freezing and melting. Freezing occurs at 0 degrees Celsius for water, but melting also occurs at 0 degrees Celsius for water. The melting point and freezing point are the exact same thing. Now, which of the phase changes actually occurs depends on if energy is being taken away or added in. So, phase changes are changes in potential energy that's stored energy. This is different than kinetic. Temperature measures that average kinetic energy, which has to do with motion. When a substance changes phase, the temperature will actually stay constant because only the potential energy and not kinetic energy are being affected. So at a phase change temperature, which phase change occurs is going to depend on whether heat is added or removed. To calculate this amount of heat, we are going to use 2 different formulas. Now, as I just said a couple slides back, phase changes have no change in temperature. So in these 2 equations, there's no delta T. And again, this is because temperature remains the same during a phase change. So if you have water boiling, it's going to be boiling the entire time at 100 degrees Celsius, even as you add in additional heat. So What are marked 2 equations? You're going to find them on the back of your reference table. The first one is always going to be used whenever you have a phase change involving solids and liquids, whether you're melting or freezing. We use Q equals MHF. Q is heat and M is mass, those who are already familiar with. Our new part of this equation is HF, heat of fusion. And again, even though this is referred to as fusion, which is usually when we're melting, we can also apply it when we're freezing because we're going to be losing that energy instead of gaining it. Our other equation is Q equals MHV. Q and M are equal to heat and mass respectively. And then HV is the heat of vaporization. And again, even though this is called vaporization, which we commonly refer to as a liquid to a gas, this equation we're going to use when we also take away that same amount of heat in order to condense a gas. So you're going to get familiar with both of these. Again, notice that these do not have delta T in them, so phase changes, again, do not occur with any type of temperature change. So we're going to go over 2 examples. Here we have a 25-gram sample of liquid aluminum at its melting point, which has a heat of fusion of 397 joules per gram. How much heat must be removed to turn it into a solid? So our equation is Q equals MHF. This is because we're talking about a liquid going into a solid, so that's why I've selected the HF. I'm going to plug in my variables. You could also, before this step, actually it's already rearranged, so you wouldn't need to do that in this example. We have 25 times 397, which then leaves us with 9,925 joules. Now, if we were doing this according to sig figs, so honor students, you might want to be aware of this. This would round to 2 sig figs based on the temperature and the number of sig figs, so this would be 9,900 joules. Alright, in example 2, a boy heats water to its boiling point. If he adds an additional 20,000 joules of energy to the water, how much of it will be turned to steam? So I want you to pause the video and at least write down what formula you should be using and see if you can plug in the given values. Okay, you should have selected Q is equal to MHV. I'm going to, in this case, just go ahead and fill in the values. You could arrange it to set it up to solve for M, because we are looking for how much. So how much has to do with the mass of the sample. So I plug in 20,000 joules for Q, and then we're talking about water, which if you remember, this was a little kind of tricky thing to kind of think about. We can get the HV of water because it's on the front of the reference table in table B, just like we used to find specific heat or C value. So HV is equal to 2,260. So I'm going to divide each side by 2,260, and when I do so, I get my mass of 8.85 grams. And this is correctly rounded in terms of significant figures. So we did one example of HF and HV. We're going to be practicing this a lot, being able to learn how to pick it out and apply the variables. One last thing I want to mention in this concept is something called phase equilibrium. We'll come back to this in a couple of units from now. During a phase change, if both phases exist, especially when we're at equilibrium. So if a sample is in a closed container and held at its melting point, that substance will be both melting at the same rate that it's freezing. That's why water is only completely melted above 0 degrees Celsius and only completely frozen below 0 degrees Celsius, because at 0 degrees Celsius, both phases exist. So equilibrium, this term, is a condition where rates of opposing changes are equal, and we're applying this to phases rates being equal. So finally, if you have this sealed flask, you can see I'm using the terminology to represent a closed container or sealed flask because that's a requirement for equilibrium. If that sealed flask contains 20 grams of ice and 40 grams of liquid water, and it's kept at 0 degrees Celsius, if I were to come back in a day, a year, a month, there will still be 20 grams of ice and 40 grams of water. Now, it wasn't that it just sat there, it's because equal rates of melting and freezing continue to happen at 0 degrees Celsius. That's equilibrium. Alright, so we've gone over a bunch of information, phase changes, how energy and IMFs are related to this. We've also talked about phase equilibrium, which we'll come back to tomorrow. So a bunch of information, and so make sure you take a few moments, check back over it, and then we'll get ready to go tomorrow in class.